Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk about Kirchhoff's current laws and voltage regulation. In this lesson, first we'll state Kirchhoff's laws for circuit analysis, and then we'll use them to compute voltage drops and current levels in example circuits. We'll then talk about voltage dividers and design a voltage divider for a particular application. Finally, we'll talk about voltage regulators, identify common types of regulators, and show how we can use voltage regulators in mechatronic devices. Let's start with Kirchhoff's voltage law. Kirchhoff's law says that the sum of voltage drops and rises around any closed path in a circuit is equal to 0. And that can be written in a fairly succinct form here on the left. Let's look at the example circuit on the right, which shows several different closed paths. So taking the left-hand path across the source Vs, V1, and V2, suppose that we have a voltage rise across Vs, a drop across V1, and then another drop across V2. Well, the bottom left equation shows Kirchhoff's voltage law applied to that loop. The same type of equation can be written for the outer loop of this circuit involving the rise across Vs, the drop across V1, and then the drop across V3. And these types of equations will help us analyze how much what the voltage drop across different circuit elements, as well as the current through different elements, and even the power dissipated through different elements. Likewise, Kirchhoff's current law states that the sum of current into or out of a node is 0. What is a node? A node is a junction between different branches of a circuit. So for instance, there's a node where I1 splits into I2 and I3 in the circuit on the bottom right. If we were to write Kirchhoff's current law at that junction, we would say that I1 minus I2 minus I3 is equal to 0. That's equivalent to I1 is equal to I2 plus I3. Sometimes we need to step a voltage down in a circuit for a mechatronics device. When we do that, one option is to use a voltage divider. To create a voltage divider, we'll place two resistors in series. The diagram of a voltage divider is shown where we have one resistor R1 and another resistor R2. And there's a combined voltage drop across this series connection of resistors. That combined voltage drop is labeled as Vin. If we then measure the voltage drop across just the second resistor R2, we can call that V2. And V2 is less than Vin. So if we're trying to step down a voltage, then Vin would be our input voltage and V2 would be our output voltage. The relationship between Vin and V2 is shown on the right, and they're related by the coefficient R2 over R1 plus R2. Now since R1 and R2 are both positive values, then you can see that that coefficient is less than 1, so it's some fraction. So V2 is some fraction of Vin. Why would you need to step down a voltage? Well, maybe a certain sensor requires a different voltage input than you have available, some voltage smaller than what you have available for your source. One important thing to understand about voltage dividers, one important limitation is that we don't ever want to use a voltage divider to power a load. That's because any current passing through the load, which for instance would be R2, is also going to pass through R1. When the current passes through R1, it dissipates power and generates heat. And so it's essentially a waste of power that we have available. If you need to step down a voltage to power a load, you want to use something called a voltage regulator, which we'll talk about in a few minutes. So voltage divider should only be used for low current applications, for powering sensors which maybe don't require very much current or something like that. We want to use high values of R1 and R2 in the kiloohms range to avoid dissipating too much power. How much power is dissipated by R1? Well, here's an equation that allows you, or an expression that allows you to compute that. So voltage dividers are commonly used for sensor interfacing or for reading potentiometer values, but they're never used when we want to power some type of load in some type of moderate or high current application. Let's design a voltage divider for a certain example circuit. So a certain sensor requires an input voltage of 5 volts DC. So that's specified in the sensor spec sheet. The voltage source you have available, Vs, that only provides 15 volts DC, so maybe that's a battery, for instance. We want to design a voltage divider, which essentially means we want to find R1 and R2 that allows us to power this sensor from the power supply we have available. So we'll want to take 15 volts from our source and power a 5-volt sensor. Let's look at how to do this. We start with the voltage divider equation. V2 is equal to R2 over R1 plus R2 times Vs, which is our input voltage. When we plug in our values, we can see that that fraction R2 over R1 plus R2 has to be equal to 1/3. We have one equation and two unknowns. We can pick both R1 and R2. So let's pick R1, somewhat arbitrarily, as 1 kiloohm. And remember that we want to use something in the kiloohms range here to avoid dissipating too much power through that resistor. So now, since we've picked that value for R1, we only have R2 to select. So 1/3 is equal to R2 over 1,000 plus R2, and now R2 is equal to 500 ohms. Oftentimes, we won't be able to buy a resistor at a specific resistance value. So if we need tight tolerances, we can get a potentiometer to use for R2 and tune that potentiometer till we get 500 ohms. Now typically, for a sensor, if it requires 5 volts DC, typically if we're a little bit off 5.1, 5.2, or 4.9 volts, the sensor will still function fine. We said never to power a load from a voltage divider. Instead, we want to use something called a voltage regulator. A voltage regulator can be used to power a load and is used to take larger voltages and turn them into smaller voltages. So a voltage regulator is a semiconductor device, and we'll talk more about semiconductor devices in the coming lessons. The nice thing about voltage regulators, they provide an efficient, stable mechanism for stepping down input voltages. The way they work is they'll provide a single output voltage, for instance 5 volts or 3.3 volts, for a range of possible input voltages. They're useful for powering components or even processors like the microcontroller from a battery. Here's a simple circuit schematic for how a voltage regulator might be used in a circuit to power, for instance, the MSP432. If we have a 12-volt battery and we want to power the MSP432, we can use a voltage regulator to step down 12 volts to 3.3 volts and use that 3.3 volt line to power the microcontroller directly. The nice thing about voltage regulators is if a battery drains, then it's okay because the input voltages can be in a wide range of values. And so if we have a 12-volt battery when it's charged, but then it discharges to 11.2 volts, the voltage regulator will take care of that and provide a stable 3.3 volt signal. There's two types of voltage regulators. Number one are linear voltage regulators. And they consist of something called an op-amp and a transistor to achieve that stable output voltage for a range of possible input voltages. Now power is dissipated inside this voltage regulator and it turns into heat. So it's dissipated continually during operation. So we always have to make sure that the power dissipated in a voltage regulator matches the power dissipation rating that it's designed for. And oftentimes we want to attach the regulator to a heat sink to help it dissipate power. You can compute the power dissipated in a regulator as shown here, the current through the regulator times the difference between the input voltage and the output voltage. Also important to note that linear regulators have something called a dropout voltage, which is how much higher the input voltage has to be than the desired output voltage. So for instance, if we want to have an output voltage of 5 volts, Usually we'll need something higher than about 7 volts input in order to be able to generate 5 volts output. Here's a typical linear voltage regulator available from Texas Instruments, and you can see the specifications. The output voltage is 5 volts, and the input voltage range can be anywhere from 7 to 35 volts. And has a dropout voltage of 2 volts, which is the difference between the minimum input range and the output voltage of 5 volts. The maximum current that you can provide through this voltage regulator is 1.5 amps. Another type of voltage regulator is something called a switching regulator. And this essentially switches a current path on and off at a very high rate to create a lower average voltage output than is input. Switching regulators are composed of capacitors and inductors and other elements to create this smooth output voltage. Switching regulators are more power efficient and thus generate less heat than linear regulators do. Here's an example switching regulator, also called a buck converter, that's made by Texas Instruments. And here again, we have an output voltage that's actually adjustable all the way down to about 1.2 volts for a wide input voltage range between 6 and 42 volts. And now we can generate, we can pass even more current through this device up to 3 amps. To summarize what we've learned in this lesson, first, Kirchhoff's voltage and current laws are used routinely in circuit analysis to determine voltage, current, and power dissipation. Voltage dividers consist of 2 resistors in parallel, and we'll use them in low power applications to step down voltages. Voltage regulators are used to step down voltages in higher power applications when applying power to a load. And regulators are routinely used to power devices that need lower voltage levels from batteries.